Hello, everybody. So what we're looking at now is indefinite integrals. So you'll remember that we did this in the previous section. We did a bunch of it. What we're going to be doing in this section is more of it. They're really just the same section, but you know, two homework assignments for it. So indefinite integrals. So let's remember what we know. So indefinite integrals. All right, there we go. So we know this. The indefinite integral of a function, little f of x dx, is capital F of x dx plus c, where, if you remember correctly, the big F is any antiderivative of little f. And in case you don't remember what an antiderivative is, it means that the derivative of the big F is the little f. So the derivative, I'll write it this way, the derivative of the big F is the little f. That's what it means to be an antiderivative. Okay? And we had a bunch of rules. And we had kind of simple ones, and then we had more complicated ones. I guess I'll write both. So remember rules. And I will recommend that you grab the cheat sheet from the handout section. So there's a cheat sheet. In the handout section of Canvas. It's in the Getting Started section. It's a handout section. It's the handouts page on Canvas. But of course, you can write them all down, and then you'll have them anyway. But we know this. So we know that if you're going to do the antiderivative of a couple of functions, that you can split it up and do them separately, which you don't normally bother writing it like this. You'll remember we normally just know that that means do each one separately, each function separately. You know that if you have a constant out in front, that you can take the constant out in front. That's a rule. And then after that, we had a bunch of formulas for specific functions. And so remember that we kind of had some like basic ones. And then we kind of had some like complicated versions of the same formulas. Complicated. And so I'll try to write them both here. Maybe we'll see how that goes. So for example, we learned that the antiderivative of what did we learn? Let's do like x to the n. We'll do the power rule. We learned that the antiderivative of x to the n was x to the n plus 1 over n plus 1 plus c, and that's only true if x is, nope, that's only true if n is not equal to -1. And of course you can see the reason why is because if you put a -1 in there for n, you would have it divide by 0, so that's why you can't do that. But then we could have a more complicated version of it where you say, well, what if it's like ax plus b to the n? And there are other ways to do this. There's like there's not a formula. There's a method you can do to come up with this formula, but we're kind of too lazy. So like for the moment, we're not coming up with a formula. I'm just telling you what the formula is. And it's like this, right? And we saw basically what the a does to that is what the thing is. Okay, and that can save you some time on integrals knowing the more complicated version of that. And again, this is if n is not equal to -1. Same rule. All right. And we had that, and then we had all of the trig functions. Let's write the trig functions. So we had one for, what was it? Sine x. And it was negative cosine x plus c. And then we had a more complicated version one of it, where we would say if it was sine let's say ax plus b, so b, then the formula is negative 1 over a cosine ax plus b plus c, right? And so basically the 1 over a is just the new thing, or not the new thing, but the complication. Okay, and we can do that for all of the trig functions. So we had like cosine x dx is sine x plus c. That one's positive. I'm trying to give myself a little more room, so I'm moving over to the left a little. If you do cosine ax plus b, that one was 1 over a sine ax plus b plus c. Again, the only thing that's new is the 1 over a. So we have sine, cosine, tangent. Now I'm saying tangent, but the reason I'm saying tangent is because the derivative of tangent is secant squared. And so the formula would be secant squared ax plus b, 1 over a, tangent ax plus b plus c, and so on. I say and so on, but I'm going to have to write them, so let's try to speed up a little bit. So what do we got? I got a cosecant squared. The derivative that gives you a cosecant squared is cotangent, but it's negative. That should be there, sort of. So the antiderivative of cosecant squared ax plus b, probably guess it, negative 1 over a, cotangent ax plus b plus c. Two more. We got the one for secant, which is secant tangent, gives you a secant. And then you have to do secant ax plus b, tangent ax plus b. Those would have to be the same in order for this formula to be correct. And it'll be 1 over a, not negative 1 over a. Secant ax plus b plus c. Okay, one more. Cosecant x, cotangent x. That's how you get a negative cosecant x. So then the formula, the other formula would be cosecant ax plus b, cotangent ax plus b, and that would be negative 1 over a cosecant ax plus b plus c. C kind of ran off the end there. Okay, and those are the ones that you're supposed to know. And then there were kind of two that we had to just throw in because there was no way for it to be left out of the homework. So I just said the two that I could not remove from the homework. We have two extra formulas. And the two extra were the antiderivative of e to the x dx, which is easy. It's e to the x plus c. And then the complicated version, which would be e to the ax plus b, is 1 over a, e to the ax plus b plus c. And the other one was 1 over x, and that is a natural log absolute value of x. And then the more complicated version of that, which is 1 over a ln ax plus b plus c. So again, you're not really supposed to have to know those, but you know, the homework is probably going to throw them in once or twice, and so you just have to be aware that they're going to make you do it at least a little bit. Okay. Now, this is all what you should know. Okay, so all of these formulas are what you should know. So you have to have them printed out, or you know, the cheat sheet is going to be good enough. And then what we're going to be doing in this homework assignment, which is homework 25, is just going to be basically we're just going to solve antiderivatives using a little bit of algebra. That's all. So there's nothing new in this section, I don't think. Just a little bit of algebra. Okay, so like here's an example. Here is an example. So like they give you this one. They say 9 sine x over cosine squared x dx. And so you're supposed to look at that and you compare it to your antiderivatives that you know in theory. And of course it's not on there, is it? Right? That is just not on there. And so you realize that. So you realize you don't have a formula for this. Okay, I should have written that in a darker color, but I didn't. So you realize you don't have a formula. So what you have to do is try to do a little algebra. That's all. And so on this one, what you can try to do is you can rewrite it. So we're just rewriting it. We're not changing anything. We're just rewriting it. And if you write it this way, first of all, I can take the 9 out. We know that. That's a rule. And then I can write it as sine x over cosine x times 1 over cosine x. Right? Because there's two cosines on the bottom. That's a cosine squared. And of course, the sign on the top, there's the sign on the top. So I rewrote it. And the reason you want to rewrite it that way is because when you write it this way, you can see that it's actually the integral of, well, what? What's a sine over a cosine? That's a tangent x, right? And what's a 1 over cosine? A 1 over a cosine is a secant x dx. So the integral that they gave you was actually a secant x times a tangent x. They just wrote it in sines and cosines just to make it hard to see, right? Now you can see it does match a formula. Right? What formula? Well, this one, right? You can look up higher on the page and find that the antiderivative of secant x tangent x is simply secant x plus c. So all you're supposed to do here is realize that you have that formula and then say, well, that's 9 going to be secant x plus c. Right? So the little bit of algebra that we did there was the entire point. They just wanted you to do a little bit of algebra, and then you would be able to use a formula. Okay? Let me see if I can find a different one. Another one with trig, I mean, before we do stuff that's not trig. Oh yeah, here's another one. So they give me integral -8 tangent x cosine x dx. Again, you're supposed to look at this, realize that you don't have a formula. Try a little algebra. All right, so what algebra are we going to do? Well, first of all, the -8 can come out. That's a rule. Then you have a tangent. Well, what's a tangent? Tangent is sine over cosine, right? So you got a tangent. What's a tangent? Sine over cosine. So you have sine x over cosine x times, then what? Well, you've got a cosine x. Well, what's a cosine x? It's just a cosine x. Right? So you can rewrite those again. So the whole point is you just rewrite them using what is a tangent, what is a cosine. When you do that, you see that you can cancel. So you can cancel the cosine. So you have -8 integral just of sine x dx. Easy peasy, because now you have a formula, so you're going to use the formula. What do you have to know? You have to know the antiderivative of sine x. What's the antiderivative of sine x? You look it up. It's negative cosine. And then the -8 and the negative cosine will actually make it +8 cosine. Okay, so you're just doing a little bit of algebra and then using a formula, one of the basic formulas. So far we've been pretty lucky. We haven't needed like the ax plus b versions of that. I wonder if that's going to last. Let's find out. Let's go a little bit further. So the trig ones are basically like that. Now you're also going to have to simplify a lot of powers of x. So for powers of x, recall this kind of thing. If you have like an x to the m over an x to the n, that's x to the m minus n, right? And you're going to use that a lot. Another thing you need is if you have an nth root, of x, that is a 1 over n exponent. And so if you know those two facts, this one, oh, the pink was a bad idea, wasn't it? This one and this one, you'll be in good shape. Because what you need to do for powers is you need to make sure that they're written in this form or in this form, right? Your formula for antiderivatives for the power rule, remember, requires it to be like this. That's the form you need. You need to list it as x to the n. That means not 1 over x to the n, not a root. You can't do a square root unless you write it as x to the n. Okay, so you have to write it in x to the n form before you can actually use the power rule. So let's look at one and you'll see what I mean. 5x to the 3 minus 3, fifth root of x, okay, we're getting fancy, over 5x dx. So what do? So the idea is we're going to try to apply these rules. Oh, I guess I could have listed another rule, but I didn't. What we're going to do is we're going to split this up into two fractions. So we're going to have an integral of the 5x to the 3, right? We got two things on top, this term, and then also we have this term. So we write them separately. We have 5x to the cubed, 5x cubed over 5x, and then minus 3 square root x. No, fifth root x over 5x. All of that with a dx. So you see, you split it into two fractions there, right? That's using, it's not a rule for powers yet, right? But like a plus b over c is simply a over c plus b over c. Use that rule. So we split it up. Now we want to simplify the powers. But before I simplify the powers, I'm going to write everything as an exponent. That means over here, I can't have a fifth root of x. I need to take this fifth root of x and I need to rewrite that as x to the 1/5 over 5x. And I'm still not going to do the integral yet, so I'm just going to rewrite it. One thing we can do here, I guess, is we can get rid of those 5's, right? We got lucky, 5 on top, 5 on bottom. And I guess this is simple enough too, where we could use we could use this rule, right? When you're dividing powers of x, you subtract. So this is x to the, what would it be? 3 minus 1, right? Same thing here. This is going to be 3/5, and then x to the, what are we going to do? 1/5 minus 1. Right? Now, we have not done any antiderivatives, and that's why I'm still writing my dx and my integral symbol. We're doing algebra right now. We have not done an antiderivative. So you have to keep writing the notation for the antiderivative right up until you actually do the antiderivative. So one more line before we even try. So this is x to the 2 minus 3/5 x. 1/5 minus 1. You can do that. It's negative 4/5. Do it on a calculator that does fractions, or you can do it on Wolfram Alpha, either or. So there we go. Only now we can use the formula we know, which was, what was the formula we know? X to the n, antiderivative of x to the n is x to the n plus 1 over n plus 1. And then plus a c. They all have a plus c. And then we're going to apply our rule. So let's try it. So you've got x squared, so that's going to be add 1 to get 3, divide by 3, minus 3/5. Then you have x to the, I'm going to write this one out, negative 4/5 plus 1 over negative 4/5 plus 1. And then, again, just throw a plus c on the end. Now notice that this is where I stop writing the integral symbol, right? You only stop with the integral symbol when you find the antiderivative, which is what we just did. So just keep that in mind. And what are we going to get here? X to the 3 over 3 minus 3/5 x. Okay, well, what are we going to have? We've got negative 4/5 plus 1. Negative 4/5 plus 1 is going to be positive 1/5. And then we're going to divide by 1/5, like that. And since we're doing this all by hand here, I'll just finish this off by hand. Dividing by 1/5, remember, is multiplying by 5 over 1, multiplying by the reciprocal. So like that. Then I can notice that the 5's cancel, and I get x to the 3 over 3 minus, it looks like 3x to the 1/5 plus c. And you don't have to go back to a fifth root. Like, what I mean is, at the beginning of the problem, they had a fifth root, right? And at the end of my problem, it turned out to be another fifth root, but I wrote it as x to the 1/5 instead of a fifth root. That doesn't matter, that's fine. You don't need to use square root notation for this. This is a perfectly fine way to write it. Okay. Now, the more you do these, I think the more comfortable you'll get with them, just simplifying those powers there. So yeah. Here's another example of something not related to what we just did. So I guess it's not another example, it's just an example. This has made me sad because it's the natural log, right? Remember what to do with the ax plus b? 1 over ax plus b goes to, with the dx, 1 over a ln ax plus b plus c. So I know that makes you sad to have to do it. Well, actually I don't. It makes me sad to have to do it. But you'll be ahead for next semester, so that's good. So what do? I take the 9 out, and then it's 1 over x plus 1. So the a is essentially, right, the a. You don't see it, so a is 1. So that's just going to be 1 over 1 ln absolute value x plus 1. So simply 9 ln x plus 1 in absolute values plus c. Hardest part is really just finding the absolute values on the Newton. Okay. Let's see. Now, there is a good reason to do this one right now, even though I'm not happy about having to, and that is, look at this example, because this is a different thing. Right? When you see this right after you did the previous example, you'll probably think, aha, it's another natural log. But no, it's not a natural log, right? Because a natural log, if you think about it, up here, the power rule works whenever n is not -1. When the power is a -1, that's actually this, right? Because that's x to the 1. That's actually this one. That's an x to the -1 power there, because it's 1 and it's in the denominator, and that makes it a -1. And so the only one that comes up natural log is when it's 1 over x to the 1 power. This is 1 over x to the 3 power, right? 1 over x to the 3. So that's not a natural log. So it's good to recognize that now, that this is not a 1. So it's not a natural log. Okay, it's power rule. All right, so let's do this. So how do we do it? Well, we rewrite it, right? We know how. You can take the -15 out, and then it's x to the 3 in the denominator, which is x to the -3 if you write it in the numerator. And then we're just going to use the power rule. So the power rule is x to the n plus 1 over n plus 1 plus c. So that's going to be -15 x to the -3 plus 1. Negative numbers screw people up here, but -3 plus 1 is -2 over -2. All right, so what is this? This is 15 over 2, x to the -2. Not bad at all. I feel like these are easier than the previous section for some reason. Oh, by the way, if you look in the answers, what they'll tend to do is, you know how, like at the beginning, we did the step where from here to here, we wrote it as a negative exponent. Well, you could always go back and write it as a fraction. So you could have written this as 15 on top. On the bottom, you have a 2, and then the x to the -2 is an x to the +2 if you write it in the denominator. So both of those are the same answer. Yeah, these are just straight up easier than the previous section, I feel like. All right, let's do one more of those, what are they called? Rational functions with exponents and things. 5x to the 4 minus 3 4th root of x over 4x. Hey, the numbers don't match this time. Right, so we should be experts at this now, because we've done one, right? That's all it takes. So you split it up. So 5x to the 4th over 4x minus 3 4th root of x over 4x. Then, you know, roots have to be turned into powers. So let's do that. Hey, I changed the color, but it didn't change the color. I know I could just simplify this right now, but I'm not. I'm doing it all at once. So this is actually 3 x to the 1/4 over 4x, like that. Then you need to use properties of exponents, right? The m minus n thing. So this is gonna be 5/4 x to the 4 minus 1, right? Subtract the exponents, minus looks like 3 over 4 x to the 1/4 minus 1. There's plenty of room on the right, it looks like, so come on, move. So we'll come up here. We're gonna have, what are we gonna have? We have 5 over 4 x to the 3 minus 3 over 4 x to the 1/4 minus 1 is negative 3/4, like that. And now we can do our power rule, which is actually finding the antiderivative. So this is going to be the step where we don't have to write in the integral symbol anymore. So what do? You add 1 to the power, so 3 to 4, divide by the new power. There was already a 4 there, and we're going to add another 4. All right, for the other one, negative 3/4 times x to the negative 3/4 plus 1. I guess I'll do this in 2 steps because we have to write it a couple times anyway. Like that. There should be a plus c there. What are we going to get? Almost done. So what can we do with this one? You can just write it, 5/16 x to the 4th. That's how I guess I'll write it. Minus, okay, this is going to be a little complicated looking. What do we have? X to the what power? Negative 3/4 plus 1. Negative 3/4 plus 1 is 1/4. And then we're dividing by 1/4 plus c. 5/16 x to the 4th. 3/4 x to the 1/4. Dividing by 1/4 is multiplying by 4 over 1. There's going to be some 4's that cancel, and it looks like we're going to have 5/16 x to the 4th, and then I somehow turned that into a minus, but that's, or a multiply, but that's minus, it looks like just 3x to the 1/4, right? Because the 4 is canceled. So like that. Okay. So notice how that was exactly the same as the previous version of this problem. They really are going to hit you with the same problem kind of over and over on here to try to kind of like bang that process home for you. Okay. All right. Let's do a couple other kinds, I guess. Here's one. Negative 15 on top. 1 minus sine squared x dx. All right. Now, I don't know how much they're going to do this to you, but the idea here is that you have some trig identities that you know. Specifically, you have these. So here's some identities. You have this one, sine squared x plus cosine squared x is 1. You also have, if you look them up, tangent squared x plus 1 is secant squared x. And also, you'll have 1 plus cotangent squared x is going to be cosecant squared x. And so what they are getting at here is that if you take this identity and you move the sine squared to the other side, it says cosine squared x is 1 minus sine squared x. So what they want you to do is realize that this has an identity involved. So you apply the identity. So you still have the negative 15. And this actually just turns into cosine squared x. Because 1 minus sine squared is the cosine squared x, according to the Pythagorean identity. And then what you want to do is remember how your trig functions work, because 1 over a cosine is actually a secant. Well, if 1 over a cosine is a secant, then 1 over a cosine squared is a secant squared. And so they want you to apply that here. A cosine squared in the denominator is going to be a secant squared if you write it in the numerator. So all of that is just trig identity stuff. And why did you need to do it? Because you need to get something that matches your formulas, right? Finally, this is going to match a formula we know. Now this matches a common function, which means you know the antiderivative of it. So what's the antiderivative of secant squared? So we have the negative 15. Antiderivative of secant squared is just tangent. Not tangent squared, nothing like that, just tangent. Antiderivative of secant squared is tangent x. Just like that. So the antiderivative is the easiest part of this, right? You're just matching up secant squared with your formula. Let's scroll way up here. You're just matching up secant squared with your formula right here. That's all. Hard part was knowing to use the identities. But of course, you'll know because you watched it on the video. Well, at least approximately 40% of the class will know because they watched it in the video. All right, let's do one more trig one. I feel like I'm doing a lot of the trig ones because that's where the variety is, I think, right? A lot of these problems end up a little bit different. Actually, that's a repeat. I say right before we do a repeat. Oh, I don't know. I think they're all repeats at this point. Let's do one more log one just because. So how would you do this one? The 20 can come out if you want. Like this. And what's this? When it's an x to the first power in the denominator, that's your, sad face that you have to do it. 1 over x is ln absolute value x. And if it's x plus 1, it'll be ln absolute value x plus 1. So 20 ln x plus 1 plus c. There should be a 1 over a in front, but the a is 1 like it was the other time. So that's all we're doing there. All right. Do you have anything else for me? I feel like there was one weird one. So I didn't see it here. So I did not see it. I just went through like literally the entire assignment and I did not see this here. But I'm a little worried that they're going to throw this one in, okay? So caution. Red means caution. No, red means scary, right? In a movie, that's what red means. Or a video game. Caution. You may see this. This one. Okay? There is no reason why you should know that. Okay? There's no reason why you should know that. However, if you see it, it has this formula. It's the inverse tangent. Okay? I just went through the whole assignment and didn't see it, but it is possible that somehow they throw it in there. So if they did, it would be this. And I'm not going to like do examples of that or anything, but there you go. So if you get one wrong, you might see that one. It's a formula that we didn't go over. It's not in the section, but I'm worried about it because I thought I saw it somewhere, even though I couldn't repeat it right now. Okay. So that is that. And that's definitely all of the homework. So good luck with that. I think it'll be okay. Homework 25 is easier than 24 in my opinion. So I think you'll be all right. All right, see you next time.